Hello everyone, and welcome to our channel, MooTekey. It's wonderful to have you here as we dive into a fascinating aspect of dairy science that is crucial for quality and flavor. Let's get started. Now, let's explore the redox potential of milk and its importance. We'll be understanding the critical role of oxidation reduction systems in milk quality. Moving forward, let's understand what is redox potential, or EH. EH is the tendency of a system to accept or donate electrons, measured in millivolts. A positive EH means an oxidizing environment, while a negative EH indicates a reducing one. In milk, EH depends on dissolved oxygen, various redox couples, and the pH. For easier comparison, we often standardize it as EH7, which is the value corrected to pH 7. Next, we explore the typical EH value of raw milk. Fresh raw milk typically has an EH value between plus 150 to plus 350 millivolts at around 25 degrees Celsius. Exposure to air raises the EH, while deoxygenation lowers it. The milk's matrix, meaning its fat and protein content, also influences the measured EH. A higher EH indicates a more oxidative environment, which can affect the milk's flavor stability. Let's also look at EH values in some other dairy products. For instance, pasteurized milk often has a different value, and fermented cheese can have a significantly lower, sometimes negative EH. The chart on this slide illustrates this range, showing how different products like raw milk, pasteurized milk, and fermented cheese compare, with values spanning from around 300 millivolts down to negative 300 millivolts for strongly fermented products. Coming up, we'll discuss why milk can have a low redox potential. There are several reasons. Microbes and enzymes consume oxygen, which causes the EH to drop. Natural reducers in milk, like ascorbate and sulfohydryl or thiol groups, actively lower the EH. Packaging or headspace that limits oxygen also reduces EH. And finally, fermentation processes can drive the EH all the way down to zero or even into negative values. Now let's understand the critical role of oxygen. Dissolved oxygen is the principal driver of EH in milk. Aeration and agitation increase the EH, while deoxygenation lowers it. Furthermore, when light combines with oxygen, it promotes photooxidation reactions. So managing dissolved oxygen is the fastest and most direct way to control the redox potential in milk. Following this, let's examine the role of bacteria. Lactic acid bacteria, or LABs, rapidly consume oxygen, lowering the EH even before major acidification occurs. This reduced EH environment then favors anaerobic metabolism and specific flavor development pathways. Spoilage flora also change the EH, and monitoring these trends can signal early microbial growth. The type of starter culture and the size of the inoculum significantly shape the kinetics, or the speed of these EH changes. As we continue, let's understand the role of enzymes. Enzymes like lactoperoxidase and xanthine oxidase interact with oxygen, affecting the overall EH. These enzymes may consume oxygen or form oxidant, so their net effect is highly context-dependent. Heat treatment can inactivate these redox-active enzymes, which stabilizes the EH. And we mustn't forget that native antioxidants, such as thiol groups, also contribute to milk's inherent reducing capacity. Moving on, we see the effect of pasteurization. The heating process drives off dissolved oxygen, leading to an initial decrease in EH. Protein denaturation also exposes more thiol groups, making the milk more reducing. It inactivates some enzymes, which alters subsequent redox reactions. However, post-heat treatment aeration can raise the EH back toward positive values. Next, we'll look at boiling and agitation effects. Boiling strongly deoxygenates milk, which significantly lowers the EH. On the other hand, agitation and aeration dissolve more oxygen back in, which increases the EH. The type of gas in the headspace, whether it's air or something like nitrogen or carbon dioxide, steers the EH direction. Finally, open cooling allows for reoxygenation, while using closed vessels limits the EH from rising again. Now let's observe the changes in EH during storage. In early storage, the EH is often stable, or may even rise slightly as oxygen equilibrates. Then the EH begins to decline as microbes and enzymes consume the available oxygen. In fermented products, the EH can reach strongly negative values, often between -100 to -300 millivolts. These changes in EH are actually predictive indicators of microbial growth. The graph on this slide shows the typical trends over a 10-day period. You can see the redox potential, represented by one line, generally decreasing over time. Meanwhile, the dissolved oxygen, another line, also falls, and the microbial activity, a third line, increases as these processes take hold. Coming up, we'll see the importance for quality and spoilage. Maintaining lower oxygen and EH levels can help mitigate off flavors caused by photooxidation. Shifts in EH serve as early warning indicators of microbial activity. The redox potential impacts color, flavor stability, and the oxidation of nutrients. For robust quality control, it's best to pair EH measurements with other data like dissolved oxygen, pH, and electrical conductivity. Finally, let's talk about shelf life and practical control. You can control dissolved oxygen through gentle handling and using gas flush packaging. The EH can be tuned with specific heat processes and the selection of started cultures. It's helpful to monitor EH7 to compare values across different batches and pH levels. The key takeaway is that actively managing EH supports overall product quality, safety, and extends shelf life. Redox potential management is an essential tool for modern dairy processing. Thank you. See you in the next class.